For this section, I wanted to introduce the idea of using Karnaugh maps to make a graphical representation of Boolean functions. So let's start by just showing what that means. I've got a grid laid out here for the Boolean function f. This is for just two variables, so we have variable a and variable b. And then the next thing we do is we put the binary values of a on this left-hand side, so a can be a 0 or a 1, and b can be a 0 or 1. Put that across the top to show the columns. So a shows the rows and b shows the columns. So this graphic, you can play around with this, all right? You can click on the A button here, and this shows the A region of the map. So this is where the A variable is equal to 1 across this whole map. All right, so I can remove that, and correspondingly, I can look at B. All right, so I could type this in. Here's B. The B side of the map, you can tell because the B value is 1. All right, so what would be, say, B bar? All right, make a prediction. B bar, 0. We're looking where B is equal to a 0, so we click here. That's that region of the map. Okay, so that's the basic idea. You can also represent intersections. So if I did, for example, A, B bar, that's the intersection where A is equal to 1 and B is equal to 0. Just that square. All right, so that gives you the basic idea of how you represent a Boolean function with a Karnaugh map. Let's make this now a little bit bigger of a Karnaugh map. Let's have 3 variables. We have A on this side and then B and C going across. This was a choice. You know, you can go the other way. You could put A and B on this side and C going across and you get a different shape, but you get the idea. You have to decide on one format. So this is the format we're going to use. So the most significant bit is A. That goes first. All right. You can tell where, let me clear this. You can tell where A is equal to 1. It's these 4 squares. Okay. You can tell where A bar is. It would be these 4 squares. All right. You can look where B is. B is this first position, 1 and 1. That's where B is on this Karnaugh map. All right. How about C bar? C bar is this outside area because C is the least significant bit, and this is showing up as 1, and this is showing up as 1. Okay. And so notice what we did here with the labeling. These are labeled according to a gray code. All right. So the idea here is that if you do that, you get all possible intersections. All right. If I flip this order, the intersections don't line up right. And so the Karnaugh map doesn't give us the kind of representation that's useful. So it's useful to have only one bit change at a time as we move from square to square in a Karnaugh map. All right. So for example, when I move from minterm 0 square to minterm 1, all right, only one bit would change. All right. So that's the basics of a Karnaugh map. From here, I can start putting down expressions. Here's A bar. All right, this upper half of the map. What if I intersect that with B? Well, where is B equal to 1? So I look at this. B is the first position here, 1 and 1. So if I intersect that with B, I would just keep this term. All right. So then I could OR C. All right. So C is this region of the map that's now in this blue circle. And so I have these 2 groups that show up for this Karnaugh map. All right. So the idea here is to get a feel for intersections and how product terms show up on the map. If you have, for example, in a 3-variable Karnaugh map, if I choose B, just and 2 variables drop out, I get half of the map, all right, because the other half is where B is equal to 0. All right, let's go to 4 variables and take a look at what happens. Okay, so with 4 variables, I now have A and B, all right, so A is the most significant bit, D is the least significant bit. If you think about this square right here, follow the arrow, is 0, 0, 0, 0. That would be minterm 1. I could choose a different square. What if I chose A bar B C bar D? All right, that would be like 0, 1, 0, 1, which is 5. All right, so minterm 5 shows up on the map. All right, so I think you can see why these are called minterms now, because if you have all the variables present, it's the minimal area on the Karnaugh map. All right, so playing around with some of the same things. Here is A. It's an 8 square Karnaugh map, grouping here to represent where A is equal to 1. Remember, A is the most significant bit, so this is the 2 bits where A is equal to 1. I could then intersect that with B bar. All right, so the intersection of A and B bar is this region on the Karnaugh map. All right, and then I could intersect that again with C. So C is in the middle here. C is this first position, so C is 1 and 1. So I would expect if I intersect with C, I just keep these bottom 2 squares here. All right, so your task to learn about Karnaugh maps is to play around with this idea so that you can figure out what regions are implemented onto a Karnaugh map. So it gives you some things to try. You can click on this and look at different representations of Boolean functions that show up on, say, a 4-variable Karnaugh map. We're going to get to more formal methods of how you can use this to actually optimize 2-level realizations of Boolean functions.